Hopefully the point person has passed out the packets. You should be looking at Unit 3, Lesson 6, Ready, Set, Go. Put your name on it. And the goal of this first portion is to think about conjectures and justification. So conjectures are what we think are true. Justification is where we actually give a reason we could use in a proof of why it really is irrefutably true. So we're going to take a look at these statements based on this picture, and it always helps when you're given a figure to think about how they made it. Remember this figure from before? They likely started with segment AC here, and then they made a circle centered at A with radius AC, a circle centered at C with radius AC, then they dropped EF down the middle. That gave them these two, and then they could make the middle circle and connect the points. Their first claim or conjecture is that AGB, along with these other three, are right angles. So when you're given an angle AGB traced from A to G to B, this angle AGB is what they're claiming is a right angle. Also CGB, CGD going down, and AGD going down. So the claim is that these are right angles. Now I've notated that. It's not necessarily true. We're trying to come up with a justification. Why is that true? And we could do one of our two methods of proving angles to be right angles is if they're a linear pair and they're congruent. So if I could show this triangle is congruent to this triangle, that would work. But I think the easier method here is to think about the construction with regard to EF. EF here is the connection of two congruent circles, and that's our construction for an angle segment perpendicular bisector. So if I wanted to perpendicularly bisect AC, I'd do a circle from A, a circle from C that are the same size, and then I'd drop that line down, and it's by definition a perpendicular bisector. So the justification we'll give here is, by construction, EF is a perpendicular bisector of AC. So the angles are right angles. And that's what it means to justify. It's to give a reason why it would be true. Take a look at the second statement they make. AG, find it. This bit right here, BG, CG, and DG are all congruent. Why would those all be congruent? Think about it for a moment. What was our first ever, look at the upper right-hand corner of the board, first ever theorem for showing things are congruent? All of these come from the center of this little circle, G. So they are, each one of these is a radius of circle G. So our justification is all are radii, or radiuses, but the plural of radius is radii, of the same circle. Now we come to a harder question. They want to claim that all four of these triangles are congruent. A, BG, CBG, ADG. Okay, so it's all of these. Let's put a dot on them in red here. Each of these four little triangles they're claiming are congruent. If we're going to claim triangles are congruents, then they need to fit one of the congruence criteria. Look up at the board there. Again, on the far right-hand side, we have our posters. What does it take to prove triangles are congruent? We need side, 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 angle, side, angle, side, angle, 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 side, or hypotenuse leg. And actually, hypotenuse leg might come in here because it is a right triangle, but in this case, we don't know anything about the hypotenuses. So, what do we know? Well, we know that they all share an angle. So that means one of these bottom three is a good candidate because they all require an angle pair. We also know that they have two pairs of sides congruent. These two sides in triangle ABG here, they're the same as these two sides in triangle CDG or in any of the other triangles. So for each of these triangles, we know a middle angle and then its two adjacent sides are congruent to the middle angle and the two adjacent sides of each other triangle. So our justification for why they're all congruent would be the side, angle, side congruence criteria. And then finally, statement 4 is about the hypotenuse of each of these triangles, AB, BC, CD, and AD. It's claiming all of those are congruent to each other. Now, those are not radii of any of these circles. Yes, they do come from the A, which is the center of a circle, but it doesn't go to the edge, so it's not a radius of circle A. So how can I claim the hypotenuse of each of those triangles is congruent to the hypotenuse of each other triangle? That justification's got to come from the previous statement. I just a moment ago justified that the triangles are congruent. Well, what does it mean for triangles to be congruent? It means every single pair of corresponding parts is congruent. So my justification, in this case, these are corresponding parts of triangles that are congruent. So they must be congruent. And that's the magic of proving triangles congruent. You only need 3 pairs of congruent parts, but it proves that all 6 pairs of congruent parts are congruent. Now in this case, all of the parts we needed were drawn in the picture up here for doing the proof. Sometimes you want to prove things are congruent and they're not parts of triangles. In number 5, for example, if you wanted to prove that EB is congruent to FD, well, EB in this picture is up here, and FD is down here. And the symmetry of the picture certainly suggests they would be congruent, but if you wanted to prove it, it would be super helpful if they were part of triangles, because the primary way that I prove sides are congruent is I make the whole triangle congruent, and then all of the corresponding parts have to be congruent. So they aren't a part of any triangle in this picture, but they could be if I added a line. The question for 5 then is, what would you add to the diagram to make them part of a triangle? Well, I look at FD, it connects to side AD here, but it's not a triangle because A doesn't connect to F, unless I make it. Anytime you have 2 points, it's guaranteed there's a segment that connects them. So I would draw AF and EF, and now the things that I'm trying to prove something about are parts of triangles. So what would you add? AF and EF, or AE, sorry. How might the addition of an auxiliary segment be used in the proof? If I can show triangle AEB is congruent to triangle AFD, then that proves EB is congruent to FD, because they'd be corresponding parts. So that's the idea behind justification, is we don't just want to see something and think maybe it is, we want to give a reason why it would be true. And we're going to practice that justification now on the set portion of the lesson. Turn, if you would, to page 2. And let's take a look at what they want us to do. The next set of problems all show you a quadrilateral, and then they tell you something about the picture. So based on the information, either in the diagram or in the given statement, they want you to make a conjecture about what kind of a quadrilateral this is. So If I look at this thing and they tell me that TRA is congruent to VAR, that's this triangle up here, that gives me an idea of what type of quadrilateral this might be. Now, in order to name these, it'd be helpful to remember what's the defining feature of a parallelogram, rectangle, rhombus. So if you've forgotten, let's just do a quick review. Parallelograms are quadrilaterals where the opposite sides are parallel to each other. They will also happen to be the same length, but the big deal about being a parallelogram is that the opposite sides are parallel. Rectangle is a quadrilateral that has 4 right angles, and it doesn't make any claim about whether the sides are the same length, although one of the properties is that opposite sides will be equal. Rectangles are a special kind of parallelogram. So is a rhombus. In a rhombus, we know for sure that all 4 sides are congruent. We don't know in particular about the angles, but we know all 4 sides are congruent. So a rhombus, some people think of it like a squished square. You have 4 sides congruent, but not necessarily right angles. And it also is a type of parallelogram. So is a square. A square is a rhombus that is also a rectangle. So it's a rectangle because it has 4 right angles. It's a rhombus because all 4 sides are congruent. Boy, that's tiny. Good luck with that. The last 3, a trapezoid, has 1 pair of parallel sides. We often draw the parallel sides horizontally. They don't have to be. And the other 2 sides are not congruent necessarily. They're not parallel. That's a trapezoid. The kite has 2 pairs of congruent sides, but they're adjacent. So in a kite, you have 2 sides that are the same length, and then 2 other sides that are a different length. And they have 1 line of symmetry right down the middle here. And an unremarkable quadrilateral simply means it's got 4 sides and I don't necessarily know anything about it. So this would be an example of an unremarkable quadrilateral. They're not necessarily parallel, they're not congruent, I don't really know anything about it. So if you're looking at the picture and the given information doesn't really tell you anything, then conjecture would be unremarkable quadrilateral. Now, I want you to be as precise as possible when you're given this answer. So if you say parallelogram, but you could have said it was a special kind of parallelogram called a rectangle, we would need to be as specific as we can. For the first one, for example, if they give me that TRA is congruent to VAR, I might mark what that means. That means side TR and side VA are congruent. That side RA and AR are also congruent. That's congruent to itself. And that finally the last pair of sides is also congruent. Doesn't necessarily tell me anything about the angles. So my conjecture in this case, because these are the same length and these are the same length, I think that will force them to be parallel. My conjecture would be that this is a parallelogram. I'd like you to continue through the set. Your sub's going to give you a certain number of minutes to work on this. You're going to pause the video, and when you come back, we'll talk about what to do with the rest. So, get to work. Okay, if you haven't already, flip to the back page. We're going to look at the go. We're going to use the diagram to complete the pair of angles that fits the description. So I've got A, B, C, D, E, F, G, and H here. We're not naming these with 3 letters. We're just letting A be this whole angle right here. So I want to know in the first set of relationships, what does it mean to correspond? What angle corresponds to F? Remember that correspond means if I think about one of the intersections of the parallel lines and I slide that along the transversal to the other intersection, wherever those angles land, if this is E, F, G, and H, and I slide it along the transversal, whichever one it lands on top of, that's the one it corresponds to. So F in this case landed on B. So I would say that F corresponds to B. You can also think if it's in the upper right-hand corner of this intersection, go to the upper right-hand corner of the other. I'll let you do the rest of those. Skip to 13. Alternate interior angles means they have to be on the inside of the parallel line, so between the parallel lines, but alternate here means they're going to be on opposite sides of the transversal. So if I look in this situation, C, D, E, and F, those are my 4 interior angles, and I want to know what is alternate interior with C. So what is between the parallel lines but on the other side of the transversal? That's the idea of what's being asked in these questions. Please continue and finish through number 18. Pause the video. Your sub will set a timer. Last question for 19 asks you to extend one of the sides of the triangle to make an exterior angle and label it E. To extend it, take a ruler or a straight edge, pick whatever side you want to pick, and I'm actually going to be creative. I know usually we extend this side here, but I'm going to go over here just to make things interesting. Extend it in one direction. And then label the new exterior angle you made E. Now it wants you to extend it a different side and show another exterior angle and label it F. Okay, well maybe I go down here then. Extend this side and label it F. And the point of this activity is to keep in mind that there are lots of different exterior angles for a triangle, and which two are the remote interior depends on the angle. For example, angle F here would have angle 1 and 2 as its remote interior angles, because those are the 2 interior angles that are away from F. But if you're looking at angle E, its remote interior angles would be angle 2 and angle 3, the 2 angles that are far away from it. Make sure you put your name on this and get it handed in when you leave today, and you will have more instructions on what to do for the rest of the time.